Okay, properties of elements Ba group 15, oxidation states, valence shell electronic configuration NS2, NP3. These elements towards maximum oxidation state +5. Since inert field effect increases from top to bottom, the heavier elements exhibit oxidation state +3. However, nitrogen shows a wide range of oxidation state from +5 to -3. Compounds oxidation state, nitric acid +5, nitrogen dioxide +4, nitrous oxide +3, nitric oxide. Okay, nitric acid, nitrogen dioxide, nitrous acid, nitric oxide, nitrous oxide, nitrogen, hydroxylamine, hydrogen, and ammonia. The oxidation state in this compounds and so on. What's the state of nitrogen in this compound? Covalency of nitrogen, number of unpaired electrons. Nitrogen shows covalency of 1d3. It does not exhibit higher covalency. This is due to absence of back-end d orbitals at low energy state. NH2 NP3. Nitrogen atom in ground state. 2s electron cannot be excited on pair electrons 3, covalency 3 at higher energy level. However, phosphorus and other elements in this group exhibit covalency of 3 and 5 both. This is due to presence of back-end d orbital at similar energy state. Phosphorus atom in ground state, on pair electrons 3, covalence 3, excited state, on pair electron 5, so covalency 5. Since nitrogen can exhibit covalency of only 3, it forms only trivalent compounds. Pentavalent compounds does not exist. However, phosphorus Xa shows covalency of 3 and 5 both, hence it can form both trivalent and pentavalent compounds like triphosphoric acid, uh, phosphorus trifluoride, phosphorus pentafluoride. But nitrogen have no does not exist due to the lower 3D in the nitrogen atom in the lower state. 3D is in the higher state, so it does not show pentavalent. Explain why phosphorus pentachloride is known, but nitrogen pentachloride is not known. Molecular formula and physical state. And 2 atoms 2. Gas P4, arsenic 4, stibnum and bismuth as the existing metal. Explain why nitrogen has molecular formula N2, but phosphorus has molecular formula P4. In case of nitrogen, NH2 NP3. In case of phosphorus, nitrogen and nitrogen. Discrete molecules, low molecular weight, weak van der Waals force, exercise gas, p pi p pi. In case of phosphorus, p pi pi overlap is not effective, so pi bonds are not formed. Polymerization of phosphorus occurs. It has high molecular weight and then exists as solid. Cause of p-pi overlap is effective between two nitrogen atoms are flowing two regions. Small size of 2p orbitals. Less interelectronic repulsion caused by inner electrons, only 2 electrons. Hence, both sigma and pi bonds can form between two nitrogen atoms. Consequently, it forms N2 molecules. However, p-pi overlap is not effective between two atoms. This is due to large size 3p orbitals and high interelectric repulsion caused by interelectrons. Hence, pi bonds are not formed as in nitrogen, formed as in the N2 molecules. So it undergoes polymerization to form P4. Molecule in which each phosphorus atom forms 3 sigma bonds. Formation of hydrides. Resilience forms hydrides of types like MS3's formula, ammonia, phosphine, and so on. All hydrides have lone pair of electrons in axis Levy space. Okay, these elements forms hydrides of type MS3, ammonia, phosphine, phosine, stevine, bismuthine. All hydrides have lone pairs of electrons and hence axis Levy space. Properties of hydride. Basic property. All have the lone pairs. Ongoing from top to bottom in group 15, atomic size increases, size of lone pair containing orbitals also increases, and then lone pairs gets more diffuse in orbitals so that tendency to donate lone pairs decreases and basic strength decreases. Size of lone pair containing orbitals increases, then lone pair gets more diffuse. So that tendency to donate lone pair decreases, hence basic strength decreases. Thermal stability. Strong bond to weak bond. Thermal stability decreases from ammonia to thermal stability decreases from ammonia to bismuthine. This is because the metal hydrogen bond strength decreases on the size of the metal atoms increases. So thermal stability in this order. Reducing property. In case of ammonia, strong bond, That's why slow. And in case of bismuthine, weak bond, so fast. Reducing property increases from ammonia to bismuthine. This is because the metal hydrogen bond strength decreases and the size of metal atoms increases, which favors dissociation of metal X bond. So reducing properties in this order. Lowest in case of ammonia and highest in case of bismuthine. Explain why. Okay. And why nitrogen fluoride. Trifluoride has no donor property, but phosphine form many complex. Give one example. Effective withdrawing of lone pair less available, less effective withdrawing of lone pair. Lone pair is more available, less effective withdrawal of lone pair. In case of nitrogen trifluoride, the lone pair of electron is concentrated in small orbital over nitrogen atom. The most electronegative fluorine atoms withdraw the lone pair of electron very effectively from the small orbital, hence the lone pair is not available on nitrogen atom. Consequently, nitrogen trifluoride does not exhibit donor property and hence does not form complex. On the other hand, in case of phosphine, the lone pair of electron remains diffuse in a large orbital of one phosphorus atom. The fluorine atoms withdraw the lone pair of electron very effectively from large orbital, hence lone pair is more available. And phosphorus atom consequently phosphine exhibit a donor property. Explain why nitrogen trifluoride is stable, but nitrogen trifluoride, bromide, and iodide are explosive. Nitrogen triiodide is very stable gas. It is unaffected by water and most other reagents. Acid alkali, it is only the exothermic nitrogen trihalide. The nitrogen fluorine bond is much stronger than other nitrogen halogen bonds. Hence, nitrogen trifluoride has high heat of dissociation, which makes it stable. Furthermore, nitrogen trifluoride is stable probably due to magnetic resonance in the molecule. On the other hand, nitrogen trifluoride is dangerously explosive, photosensitive, and very reactive liquid. Nitrogen tribromide and triiodide are known only as they are unstable ammoniates, such as nitrogen tribromide, ammonia, and triiodide ammonia. These halides are endothermic. It means nitrogen halogen bonds are weaker, hence these molecules are very low heat dissociation, which make them explosives.